Good morning, colleagues and students. Welcome to this Dean's Distinguished Lecture given by Professor Yuguo Li. He will talk about designing a resilient city for climate change and pandemic. Professor Li is a chair professor of building environment at the University of Hong Kong. His research spans city climate, infection transmission, and sustainability engineering. I think we first met in one of these maybe outdoor air quality climate symposium in Hong Kong. So we knew each other for quite some years. Welcome to KAUST. It is his first visit here. So his team investigates ventilation requirements for mitigating SARS-CoV-2 transmission and exploring resilient city design strategies and technologies. Professor Li serves as a member of the World Health Organization Infection Prevention and Control Guidance Development Group for COVID-19 and is the founding editor-in-chief of Indoor Environments, the official journal of the International Society of Indoor Air Quality and Climate. So there's a change of the journal name, used to be Indoor Air. So for those of you who publish in that domain, it's the same journal, but with a slightly broader focus now. He has received a number of awards, a fellow of the Hong Kong Academy of Engineering, and also some international awards, the Patent Cover Award, the Guangdong Engineering Science and Technology Prize in China, and the Medal of Honor from Hong Kong government, the Louis Bill Holiday Distinguished Fellow Award, the Rebirth Gold Award, Gold Medal, and he's also an honorary doctorate from Airborne Universities in Denmark. So without further ado, please join me in welcoming Professor Li.
Thank you. Thank you, Dean Jack. Really pleasure to come to this wonderful university and the kingdom. I like to talk about a big topic, and for a very simple reason. I see the world facing, more of us facing some really big challenges. Pandemic is probably minor compared to those big challenges. Pandemic I have been working on for probably more than 20 years. And when I joined the University of Hong Kong, that was the year 2000, 2003, we had SARS. And that's how I ended up with a fluid mechanics background. So resilience probably simply mean you go to library, dictionary to adapt, recover, and thrive, even there is a change. And to me, that if all this existential crisis continues, and if the climate change is too significant, I guess there will be not possible for global even resilience, if it is too serious. So this is why it becomes important to look at it. Many of us have different views, but I so-call them three crises: global climate change, environment pollution, and biodiversity loss. I think you have to handle all of them together. So I will come to that point later on. The first on pandemics. Pandemics, I feel that look at your vision or the work, and there may be some connections, so I will do that later. So pandemic frequency increases according to my colleagues in the university. And I think a few days ago, there was a study of avian flu in the US, and people suspect that could come up again. The climate change, if next time comes, if this whole thing goes worse, and there is a chance for our capacities of response to be reduced. The more we look at today what's happening, perhaps some worries in front of us. For the SARS pandemic, actually for the whole year, there was very little thing we could do. So then the question is, if possible, to dilute, stop it. To me, we failed in the pandemic, but we recognize the importance. So I think you will see later, the trick is this super spreading. So I will going to talk about a bit more ongoing work, how to handle it in our modeling in order to provide a policy. I'm not of the view that we rush to develop a policy, as many countries are doing. I think it's dangerous. It will cause climate change problem to be worsened. For instance, you demand this building to be ventilated at much higher rate, and that's money and energy. The positive thing, perhaps also in this country, it's possible to control it. In the first year in Hong Kong, we were able to go to offices every day. There was no problem. We were constantly being attacked by imported cases. So if you look at this diagram, you'll find that we lost the war perhaps early 2022, something of March, then the whole city was full of cases. But for the 2 years in a row, actually we had a small number of cases, less than 10,000. And we were able to go to work daily, and this means every single case is imported in, defeated by purely, mostly non-pharmaceutical interventions, dilution, wearing a mask, everybody wear a mask. The problem is that in this world, there are some culture people will find wearing masks is difficult. You have to recognize it's a reality. So that the question is it possible to do something with COVID-like pandemic by dilution and distancing alone? If that's possible, because it takes time for you to develop vaccination and treatment. So how much we can do? So what are the tricks? What are the mechanisms inside? And that's my key. A little bit for people without background and with sometimes confusion. So there's something called a outbreak, means one setting, one source case of people infected, number of people infected in that setting called outbreak. And if there are many outbreaks consequentially, and then it spread in a community, is called epidemic. And if it is globally spreading, multi-continent pandemic. So outbreak, in one outbreak, if you make sure there is no one infected, that will be fine. Less than one person infecting that person. But in an epidemic, pandemic, and then we have this basic thing, basic production number. So one case, the number of secondary cases is caused. And if everyone in a single case do not lead to a new infection, then it will die down. If you only in the one infection, it will never grow. So we aim for less than one. And then the question comes up, obviously, should you control outbreak? It will be very expensive. If there is a super spreader, you will never be able to control an outbreak. All the outbreaks have no infection, but you can do it for the entire community. So this is number one. For instance, if R equal to 1, first generation, at 0 generation, you have 1, first, second, 5, until 5th generation, you all have 1 case, add up together, 6 infected. If you have 4, and then it's double, triple, quadruple all the time, so you end up by 5th generation, you get 1,365. So you have some curves I just randomly draw, and obviously your target is make sure are not equal or less than 1. So this is our target. Ventilation is probably the most common mechanisms to control. You supply outdoor air and distribute, most important second term, in the space. So if we dilute, then if you have a source divided by a number of ventilation air in amount of air, then you get CO2 500 ppm, outdoor 400, indoors 400 plus 500, 900. So we commonly use 1,000 ppm as a criteria. But you will see later, actually our problem is a little bit more complex than that. You may wonder, there are already existing standards like ASHRAE 241, They produced that with Biden's administration. They really rushed to want to have one. And I feel it's a bit in a rush. And for instance, ventilation, normally we typically supply 10 liters per second per person. Now we do 25 in many cases. It's overdone. It can be potentially overdone. And if you widely spread, then the energy for air conditioning will increase substantially, depending on the method you use. So, however, also in this standard, they do not consider super spreading. They did not even quantify the relative impact. So by doing dilution alone, how much you can reduce the impact, and then you can justify whether you need to wear a mask. And then also, we'll see later the importance of short range airborne, which I call the short airborne. The airborne transmission within a short distance. In this field, because of difficulties to quantify the amount of infectious virus needed to cause infection and the difficulties, and I just talked to Professor Payne about microbiome genomic genome sequencing. And so people actually produce a little concept called quanta. And this quanta produced by infector QL. And somehow you are able to derive equation, and there's a lot of things students have went through. And in this equation, the average probability of infection, which might be approximated as a ratio between the number of secondary infected cases, secondary cases over the number of susceptible, the number of people can be infected, which is only a function of QL, dilution rate in the room, inhalation rate, and time. So for instance, if you know all these numbers, actually you know the data already. So if in a classroom, a larger room like this, 30 people, everyone gave 10 liters, so the source is 100 quanta, which means they produce 100 portions of infectious viruses. And then with a certain inhalation rate, when you sit there, is about 0.1 for adult. And exposure time for 2 hours. And everyone gets 10, so it's 300 for 30 people. And then you find out the infection probability is 4.4%, and 2 people will be infected. So in order to make sure 1 person infected, less than 1, you need more than 20 liters per second per person. So in theory, if you know all the numbers, you can predict. The trouble is, all constant here, they are variable. In particular, the quanta. We have super spreader. So I'm going to not give an answer. It's on the way to get there, I think. And I have been confident for this number for the last 2 years. But the more problem you describe. And some of you might be familiar with this outbreak. So in this outbreak, there was this purple person, aged lady. On her side, there was her grandson, and the 3 families, and you find all by the window, and some people got infected. This was probably the first case in the world people know. So we were able to measure everything. We found out ventilation rate was very low. We normally need 10. They give you only 0.9 liters per second per person. So you conclude poor ventilation leads to outbreak. There was misleading information on the internet. Air conditioning caused intubation because you saw that this one has they call the fine coil units in air conditioning, 1, 2, 3, 4, and 5. Actually, do you know what the fan coil unit does? It's cold air, chilled water goes to the fan coil, and the air goes to the coil and being cooled down, recirculated back to the room and all forth. Coil, they are actually a filter. So they can filter out 20% of viruses. So you add all together, you find out this room produced dilution rate 7.7. Very close to commonly we use 10. So then you wonder, it's the super spreader that caused the problem. So this is very significant. So this also means that we have to consider all removal. Now we call it One Health. One Health means you consider all earth, soil, everything. I say one dilution. You have to consider everything by CO2, by the things that can remove PM 2.5, you can remove by aerosols. And the aerosols can also be deactivated. So you have to consider them all. And if you only consider ventilation, that's wrong. And the fact that the bioaerosols share some of the removal mechanism as CO2 means that removal by aerosol has to be a part of indoor air quality overall management. Otherwise, you duplicate your effort. So this is very, very important. And all the thing together, now I finally decided it's called clean air equivalent, like a coal equivalent thing, CO2 equivalent things. And that means total amount of clean air you do. So actually offers a number, 25. And I don't know about that number. So, sorry for it. So now you have one outbreak, you have number of people infected N eta, and then you have a number of settings. This person visited, the add together is a number of secondary cases by this person. And you can actually find out distribution of this number of persons. So every person distribution number of cases, the secondary cases, 10, 20, 30, 40. For SARS-CoV-2, amazingly, 70% of people, 72 with this calculation, don't infect others. So 0 cases for 72%. And then, some people infect a large number of people. This is called super spreading. And it's characterized by this dispersion coefficient, can be properly defined. Here we don't, called K. K value less than 1 is super spreading events. And that's very, very important. My K message in the next few slides. K equal to 0.1. Why? We never have such a super dispersing things. Normally, this negative binomial distribution, that if this things like this, then it's over dispersed. That's what we have here. But if the K equal to infinity, then you have boson distribution. And you will see later for influenza, K equal to 1. And that got us into trouble. By realizing this trouble, I think it's very important. For influenza, R0 equals 1.2, which means influenza is less infectious. But it's amazingly, their K value is large. And then for SARS-CoV-2, it's very infectious. I mean, for ancestral, from Wuhan, 2 point something, and K equals 1.1. Actually, even for Omicron, probably 10. So it's more infectious. Why the K value has become small? Amazingly, you can write an equation, and you can derive, so that if you know K, R, no, then you can find the percentage of people who are not infectious. So you find out, okay, for influenza, 45% people don't infect others. For SARS-CoV-2, 72. That's a little bit of problem. Basically, SARS-CoV-2 is more infectious, but more people did not infect others. For influenza, they are less infectious, and eventually, the K value is very large. And there are at least 2 papers in Lancet and talk about this. I think there's no answer. So eventually, I figure out that this might be the K. If your model do not predict this characteristic, then forget about it. You will never get an answer. So you have to be able to tell why SARS-CoV-2 is more super spreading than H1N1. And then what are the mechanisms? And this goes back to my, this almost 20 odd years to study, I think, SARS 2003, and later on we have MERS here, and then we all involved in those studies. I think the most significant, our little work, is I summarize in one sentence. Short-range inhalation, which I call the short airborne, predominates. In close range. Everything close short range. It's not a large droplets. So this, fortunately, the work was finished just before the pandemic, and eventually on 18th April 2024, WHO produced a new set of terminologies. I think you have to get name right before you act. So, and Director General also made little remarks. To know the significance of this, I quote there what they wrote. The director says, this revised terminology must now be used by WHO and other public health agencies across different pathogens in different settings. And the chief scientist says, this allows us to set a new path. So we are working on this. There will be a new meeting in May, around the end of May, to discuss about how we move ahead that get a new set of public health measures. And our work is also for this purpose, probably little contribution. Anyway, that's for ventilation. For distancing, very often people have this diagram, you know. This diagram is wrong. You do not infect each other if you're all facing front, as long as you don't turn this. There's no exposure to, you will not inhale other, apart from there's wind blowing. It's the face-to-face interaction most important that you inhale. So one way to remove this, you keep distance. So my students, many years ago, 2005 or something, she provided evidence for why it's 1.5 meter. You can also wear a mask. The effect of wearing a mask is more sufficient. And if you have symptoms, you wear a mask. But sometimes asymptomatic cases also infect. The question is, how do you quantify? And actually, for instance, you can reduce household contact. That's very difficult. And you can wear a mask. Or for your school children getting, they like to be together, and you close the school. Minimize. Actually, closing school is not only about maybe short range. For influenza, effective. Many studies show it's probably short range. We'll see later. Long airborne, also similar cases. You can do a lot. Let's say that you want a minimum. Then you have to know what is the minimum. If you want a warning, you have to know what is the minimum. Otherwise, you cannot tell. Of course, before people have maybe a low-cost, real-time determined monitoring of bioaerosols. So far, we are unable to do so. I give you a very simple argument. I don't think it's written anywhere. Why the two are different. So we mentioned for SARS-CoV-2, 2.5, K equal to 0.1. And you can derive another equation, which I have not seen everywhere. And you find out, oh, infection risk 3.8%. And then if you see influenza virus, they will look like something like this. And on the bottom here, the secondary case distribution. If K equals 1, then you find P 45.5%. Infection risk for influenza is much higher. It's one order of magnitude higher than the SARS-CoV-2. But the R0 is small. You know what that tells you? It must be influenza. They only infect small number of people potentially. And those small number of people must be in close contact. So if this is the case, then I can conclude very simple. SARS-CoV-2 predominantly long range and influenza short range. So simple. But if that's the case, unfortunately, we only realized not a few months ago. And if that's the case, then we should be able to do something about it. Otherwise, we are not there. So this is my hypothesis. We are very close, but I don't think there's a need to present you real data. I think that if for influenza H1N1, let's say R0 1.2, probably 2/3 contributed by short airborne, and 1/3 by long airborne. And that's how we can explain that differences, less super spreading. For ancestral, maybe short range is still high. 1, unfortunately, close to 1, 0.9. I think our prediction is about 0.9. And then long range, 1.5. Add together, 2.5. For Omicron, again, long range is way ahead. It's probably 8 or maybe 9 even. So short range will become more important, but less relatively important. Any epi models must predict these differences. So that's why I'm a little bit suspicious of this SEIR model, the traditional SIR. And I feel that this new way of looking at things which may be more reasonable. We are working very close. We have done a lot of predictions using this hypothesis. And if that's the case, then you know for Omicron, but even the close range, you cannot control it if you don't wear masks. If you wear masks, you can. But Omicron is very difficult because for such a RNO, the ventilation requirement will be big. It's very large. So that's why Omicron is spread just like hell. You cannot control. I will, because we have a few droplet people and check real expert on aerosols containing particles. So actually this, when you exhale, WHO with a new terminology called infectious respiratory particle, RRP. RRP has two sizes range. In short range, large. It can be 100 can be inhaled, micron. They can contain multiple variants, infectious virus. It's amazing. This is amazing if you read that paper. But in long range, only small ones involved. And the small ones actually maximum for majority, 95%, I think, contain only one. So when you inhale one droplets, one virus, and infectious, if you inhale large ones containing 100 infectious viruses, same, only infect one person. And that's very important when you quantify those response parameters. That's what we have done there. And a little bit of math distribution thing. And we come back to quanta. This very important concept is one portion of infectious viruses. It may be one RRP with one variant, or maybe one RRP with multiple variants. Only a whole number of quanta is possible because you cannot have, I don't know, there may be a possibility I get to open why half quanta from her and quanta from you add up together as one. But this physics, because we are mostly considering one infectious source so that we can see whole number. With this kind of thing, you can do a lot of things. Actually, once you know these basic assumptions, you can predict quanta distribution. Because this is log normal. Log normal. There's a few things to know. How do you get this distribution? I can do it with 3 methods. I hope Geno people will offer a new method. And number 1 is you have viral load, you have conversion, but you cannot know what is conversion from viral load to quanta. Then you can use our data because we know 70% of people don't infect. We know what happened. And so by doing that, you find the location of distribution. And then you know that this whole thing, practical, we have 20 outbreaks, we know the quanta distribution. They cannot be more than 2,000, for instance. And then you know the range. So roughly you get, see, the viral load method is this one, the yellow one. Number 2, I know all the airplane outbreaks. Airplane, you know very well, environment data. So you find the blue data, little bit different. I have a 3rd method using animals, not published, not presented. It's very also interesting. They all agree, roughly. I think they need more analysis. Anyway, then next question, what is short range, short airborne? What is the quanta? Actually, with the method we just described before, I call them short quanta, long quanta. The ratio between the two will be simply a function of viral load. And by doing that, I somehow want to call them universal quanta. It's the same file. If you assume everything is done by droplets, everything is emitted from upper respiratory tract, then it's 1. So anyway, this may be too fast, but we can go on a little bit later. So for this part, I know it's very heavy. And I want to see that there's so many, there's one important parameter is called dilution rate. The idea is like this. If you do not know what are your dilution rate in existing buildings, how can you know how much you want to improve? It's impossible. So you have to know the existing buildings. You know what, these little areas, you cannot get big fundings. In the world, total number of buildings being measured, I think Your team also, Alexis Lau, also measured some. Total, we measure less than 5,000 buildings. There are billions of buildings in the world. Impossible. And one important thing, they also change in time. So you need real time. To me, to be able to monitor, have a low-cost, real-time, privacy-proof monitoring system. Let's say you call it now KAUST. You can predict what happens in the next few hours. Crucial. We are working on that. I think the sensor people can find it. I have a project to do that, but there's no time to present that sensor. Interestingly, if you believe what my presented model, then with Hong Kong infection data, we can predict dilution rate distribution in all Hong Kong buildings. We probably have 7,000 high-rises, I don't know, totally 3 to 4 million spaces or more. I mean, we have 7 million people. Divide by 2, probably roughly. Everybody have a home, this one space. So then the distribution like this. We know the infections very likely, we'll see later, is happen in poorly ventilated spaces. And these two over-ventilated. I mean, it can be possible. Only see the number of people in this room, not large, is still ventilation. They vary per person. So I can probably state that these are the dilution rate distribution in Hong Kong, but I do not know which specific building is poorly ventilated. This is trouble. So short distance, short airborne. Short airborne is complicated by the way you move your head, you nod, you say no, and this different time, how do you quantify them? And this smart student, Liao, she said, oh, I define a ideal equal height face-to-face scenario at a distance, 0.4, 0.7 meter, or 1.5. Once you do that, you can quantify that. So she actually was able to find the time Hong Kong people meet at home, in schools, offices, very little. You can ignore that. So only 2 environments probably, maybe hospitals. We have not included hospital. So it's possible to determine those parameters. It's very important. They are not there. So I think I had a postdoc, Zhang Nan, the man there. So he's measured a lot of short range, the distance between people and your head relative location and something like this. Yeah, you can do a lot. So it's equally as difficult as dilution rate if you want to do it. So now I think we have a way to do it the best way from the benchmark. So just imagine import a case into a country, into a city. He or she might go to any of the spaces. And if these spaces, if he is a super spreader, he potentially can infect few more people. If the space is very well ventilated, don't worry. So everything is probabilistic. And then if he successfully infected on the bus, and the lady on the bus may go to elsewhere, that's the second generation. So you need to consider all this generation and so on. So I think this is what we are doing. And for in such a dilution rate in Hong Kong, you find the red one cause more than 10 people, 5 people. The blue one, less than 5 people. And you can get all this huge number of data, which I hope in summarize. So my message is that there is a possibility to go get into those data. Not there yet. And so in the world, you're getting data, I'm a little bit worrying. Our team has been recommending this for during the pandemic. I think if you ensure everyone get 10, and there's one thing I did not discuss. If the number of people is less than 10 people, you need 100 liters per second per person. If you have space corridors, you need to do more. So I will not discuss more about the pandemic. I like to talk about little dome city. Anyway, if we can build a dome city, very large, we'll see later this city will be infection-free. and offer some new possibilities. One of the aims I hope the community hear your view. Buildings, to me, are not built for comfort only. If you look at history, look in this Arabian Peninsula, or the jar I know is invented here. It's for storage. We store our food, our clothing, our stools, everything we store. It's become part of property. And buildings and cities are all built with material itself is a property. And they are just like our clothing, everything. They do not last long. And that's got into problem. I think between last 100 years, our consumption of materials increased from 20 to 150 tons per person. Exponential growth. And there's a lot of problem with overconsumption. I don't think I can do anything. If there's any social science people listening the talk, you may have a better way. I feel it's not where production is, it should be where the consumption is. The world now ecological footprint, measuring the amount of land and water needed to support one person, average 2.6. I think US is something around 8. This country is not low, China is not low, Hong Kong is not low, but the biocapacity is 1.7. How can you half reduce that? If otherwise, we are talking about, it's not one earth, we are talking about small solution. Dean Check would know that I also work on urban climate in Hong Kong. I eventually give up because I think the more I work, the temperature continues to rise, energy continues to rise. There's no way you get disappointed. So the major life provisioning system physically might be cities, because cities consume most of the energy materials. Building solutions do not work if majority buildings are not improved. You can improve 1 or 2 buildings successfully. Many people done that. Newspaper in Hong Kong reported our success story all the time for the last 25 years since I have been there. For discussion, more philosophical. To me, for the last 5,000 years, I think somewhere close here, where the enclosure with a door was first invented. Our cities have been built only by simple stacking. If you want high buildings, you put one more on top of another. If you want more buildings, you align them along the street. What you created? Nothing. Actually, still individual buildings. Buildings are for privacy, but not free from climate structure. Envelopes add up. You know the heat transfer is UA delta T, the area of the surface, multiplied by heat transfer coefficient, multiplied by temperature difference. The more air you have, the more heat. So add up, everything add up. Structure and material demand materials. High rises, you need more. You have lateral loading. You have earthquake. Heat, moisture, pollutants trapped in urban canopy. And in one of the problems in Hong Kong I handle is urban heat island. Urban heat island in Hong Kong is very different from elsewhere. It has an urban heat island at night, but cool island during daytime. Daytime in Hong Kong is cooler than outside. And I was, talking to our Hong Kong observatory. It's a little bit intriguing. But putting in the short, and in Western cities in the US, they have full day, whole day. Explore cities, whole day, 24 hours heating. In temperature is higher. So for some of you, I think Jack might have seen this. I thought this stone forest in China is Hong Kong high-rise buildings. So some years ago, I sent a student there to measure it, So what is temperature in this thing? This is 30-meter tall stone structure. There's no anthropogenic heat, no cars. Only some number of tourists. And you measured the temperature inside this whole thing. And then you measure the temperature outside of it. Only 1 kilometer away, 2 kilometers away, you have this open space, green. Stones are not many. You find the temperature similar to Hong Kong in high rise. And this, when you read this kind of diagram, you feel disappointed because the temperature profile is dominated by building structure. It's the city structure you made it. Nothing you can do about it. The only thing you don't want heat change, remove all the buildings, then there's no city. Disappointed. You feel you cannot do much. There's one way you can do. I mean, in this part of the world, your building is elevated. Elevated by 10 meters. We proposed this solution. I wrote a proposal to the Hong Kong government 2 times, all failed. Nobody wants to elevate the buildings, it would be very, very expensive. So, future city design probably can draw some inspiration from the form of life. There are 2 things with life important, I realize. One is every single life, single body, autonomous. Number 2, homeostasis. You keep a constant environment within your body so that the organs work. Actually, for organs to work, the most important materials are still new. That's the basic thing. So cities are different. Multi-cells evolution, I think, is very important. They somehow came up with autonomous body. But cities, we have multiple buildings, multiple bodies, So I think cities, in this regard, probably not an organism itself, the existing cities. So we need to do something. Every building need to fight for their own safety, the rain, the wind, the flooding, and you need to change materials every 60 or 70 years, 100 years. They need their own insulation. They need their own air conditioning because they lack of homeostasis for the city. So they are not protected. And I don't know if you have seen this termite mound. The termite, 150 million years, sorry, not years, they built big structure for nothing. They built chimneys above, they all for a stable environment for their homes, their gardens, for agriculture, and they are there for not far away from here. In Africa, you can find many. And I always dreamed that Egyptian might have mimic. I tried to find evidence, there's no evidence. Actually, the termite mound structure and Egyptian pyramid, the structure is very similar. I don't know why. Anyway, this gave me inspiration, and looking back, so-called green building follow nature. Nature ways is autonomy, city structure, and this is square law. You want the same volume, the area should be minimum. That's circle. So the circle, nothing new. And Buckminster Fuller, big thinker in the American architect, trained not to be an architect. And he developed this. Every now and then you find newspapers will talk about it. And I found it intriguing. It's simple. One circle, you build a hemisphere, double the area of the ground. So the maximum area is 2 times. In Hong Kong, 1 area, square meter, build 10 meter square envelope. So now you reduce to only 2 times, you can reduce significantly energy consumption. And you can add more, I think more, you can, no wind loading, you can use less materials. Now is everything homeostasis, the building will last for a long time, if not forever. It's like a piece of paper, you can survive long. Buildings and streets will become interior structure. If that's the case, you and I can build a dome. I have a small team, and I just want to tell the world whether a Fuller's dome can be built. Feasibility, not to design one. So it has to be above atmospheric boundary layer, because I want to draw the air from upper coming in. So air conditioning in Hong Kong will be much cheaper because up there is drier and more stable. There's no 24 hours variation, much less. Air conditioning system will be very efficient. I call them super conditioning. And there are many, many more. I mean, we can discuss. I'm totally drawn into this little idea, and I cannot get out of this. So I draw a AI diagram. That's look like. That's our model so far. And this one needs a number of people. I mean, I just give you a quick idea. So in this city, if you have no roof, the sprawl city, let's say they use 4 times of material, very rough, and then high-rise city halved. Hong Kong is very efficient in using materials. And New York the same, New York City. If you put a roof, then sprawl city is hopeless because you use much more materials. Because the roof is wasted. You only have a few new buildings within it. It's not good. But if it is building is high-rise, compact as in Hong Kong, wow, half everything, minimum. My estimation is very, very conservative. Energy will be much less. It will be probably 90% reduction or 80% reduction, as this one Fuller already said that. You know, if this is the case, something you and I cannot ignore. But it's too big. It needs a lot of people to work on. I hope to present a little comparison to the line, if you don't mind. I think the line is a great idea, but let's say that the line is 170 kilometers, 500 meter tall, 200 meter wide. So it gives you 17 kilometer cube volume. Equally, I do the same base area. They produce 34 kilometers square. I mean, 170 multiply what, 0.2. So you get amount of areas in 34. If I for the 34 kilometer square land area, I can build a dome. See, I do 3.4 kilometers, too high, okay? You will not do this high. So eventually you find out that you expose the area only 53, 1/4 of it, 1/4 of the 200. I think this is significant reduction of energy. Only 1/4, you save 75%. There are many, many different things you can do with it. The distance between people, I mean, mean distance 85 kilometers, now in the dome is less than 6 kilometers. So, I mean, you can travel everything easy. The dome can be by walking. Probably, if there are any people interested, happy to collaborate. There's a lot of things to work on this, and I think Ms. Zhou Wan, she is interested in the climate. And that's why we come here for this. And there, for people with a background in architecture, you know Le Corbusier, another modernist, and he has a 5-point of architecture, which I don't. I mean, he produced this beautiful architecture there on the top. So I offer, summarize this roof city 5, hazard-free. Once you have the roof, the city is free of wind, no dust storm. You can walk, you can go out anytime. Free design buildings, architects can do whatever they like. Freely design, modular design will become possible. And I think efficiency will increase, solving the construction low efficiency problem forever. There is no rain. There is no large temperature variation. Totally path-safe design. Architects can design the buildings with open windows, like some of the buildings here. And free choice or minimum use of materials. I think the walkability becomes the issue. When I walk around here, I added that. I think people can go out. I look at some of the building design. When you have shade, people come out. And under the sun, Here I feel there's no crowd and no people on the street, open street, I mean. So, and most importantly for this city, there will be no one to be homeless. It's a little bit problem challenging, but so quick summary, Mr. Dean. Dilution distancing alone possible to do a lot of things. There's need more work to be done, and roofed city form may offer a solution to the half Earth we need to consume everything half, because everything is halved in this city, and also for COVID-like control infection. So there's many big things about this idea. And for the city design, we need civil engineers. So I have recruited 2 civil engineers, 2 more to come this summer, no, next year, and 2 postdocs to come. Zhao local climate, interaction of the dome and the weather, and then there is somebody needs to design this air conditioning system for this big thing. Once it's done well, everything else you don't need to do it. And I have to work with the architects and my civil engineering people. And the last lady, she is an architect, so look into how a building can be built in an environment where you have 4 seasons of spring. You don't have seasons anymore. So there's a lot of other things, water harvesting and a lot of new possibilities. And for the infection, I have many, many people. I only listed the latest who have been working in the last 3 years. And most of them, they are still here. Thank you very much.
Thank you, Yuguo, for the thought-provoking talk. So floor is open for questions.
Thank you, Chuck. Thank you very much for this interesting talk. We don't usually sort of listen to talks like this, so this is refreshing. When you started talking, the first thing came to mind is the SARS epidemic that happened in Hong Kong, and I wondered how much did Hong Kong learn before COVID hit, in a way. So I think it was 2003. Yeah. Now, it was sort of contained within that area. Did the authorities sort of learn anything that actually helped in the data that you produced during COVID? The other question I have is about, I think, Japan in particular, when individuals wear personal masks every time they feel that they have sneezing. And are the statistics from that country different from the rest of the world because of the personal responsibility over infection adults?
Yeah, I think Jack was there. During the pandemic, I seldom see anyone on the street without mask at the peak time. In Hong Kong, everybody wear a mask. This means basically, literally everybody. I have never seen anyone, because I travel by subway to my work every day. So in East Asia overall, people, probably due to SARS experience, and very likely this part of the world will do the same. Do you have anything to add?
Well, I mean, if I could make a comment, I mean, actually, people will look at you if you didn't wear a mask. Yeah, and they would stay away from you in public transportation. Some of you know that I love Japan, but a lot of things, I think part of it is that Hong Kong has quite some Japanese influence in terms of visiting. So in Japan, even for my flu, it is the custom being courteous that they wear masks. So we adopt that culture too.
And then you made a very nice comment about the impact of SARS. And I think the SARS basically made airborne transmission to be a topic. So we look at those outbreaks, it's amazing, it's too big. I think we thank Hong Kong government for making very detailed analysis and made our work possible. But one of the important of that preparation, that's why Hong Kong was doing well in the beginning of the pandemic, is that in 2004, because we had one doctor died It's a lady doctor. Everybody cried, actually. So the government built 1,400 SARS ward. We call SARS ward. And I designed most of them. So that with our laboratory work, and those SARS wards being maintained regularly over all these years. So during the pandemic, suddenly being used. If you have less than 2,000 patients in Hong Kong, we handled it very well. So there's no problem in one city, you know. And this is amazingly, only when we are over 10,000, we started to worry where to put them. Because below 12,000, we put them in the Asian Expo, very high ceiling space. So I think Hong Kong health agencies, they have done a good job. And they have a regular meeting over the last 20 years, actually before pandemic. We have a scientific committee for infection control. I've been there all the time, and there was always reviewing what's happening in the world. Preparation may becomes crucial. I worry a little bit nowadays because elsewhere, a lot of places, people, I think somebody today, I talked to Professor Payne and using the word COVID fatigue. So, yeah.
Just add a little bit. Part of the success of Hong Kong is because there have been so many high-rise buildings. So the architects, the civil engineers, and the mechanical engineers. So we have a good group of people, of course, including you yourself, who have been working together. So the ventilation business professionals are really there to help out the government policy. You have a question?
Yeah, just a couple more if I can. There's a major problem with airplanes, mostly because for energy savings, they don't circulate as much air. So they circulate a lot of the air. Is the infection rate much higher in airplanes as compared to a classroom or other place?
Not really. It's a good observation, worry. I also worry about it. And somebody got it wrong, got it right. This idea is very simple. That's why I recommend 10 liters per second per person. On airplanes, normally you give 5 liters per second per person because it's too expensive.
Exactly, yeah.
And then the filtration contributed the rest 50%. So 5 to 5 is 10. And average is 10. So when you have a distribution, you find the mean is around 10. There are about 20 outbreaks of COVID earlier part. The R0 is less than 1. Actually, I made a presentation maybe 2021. If all the buildings are diluted as good as airplanes, there would probably no pandemic. So that's the argument. It's not because airplane gas is right, simply because their filtration is very effective.
Okay.
Their air quality may not be. I mean, we are talking about removal of aerosols. So you go to airplane measuring aerosols, very low, very low. I guess some people in Hong Kong, frankly. So that's it. That's it.
I mean, Bill's saying the airport is perhaps worse than the plane, is it? By the look of it, yeah.
Yeah, but on the other hand, on the airplane, it's too close to your neighbors, then you have trouble. Short airborne.
If I just one last thing, I mean, the sort of roofed city concept is interesting as a concept, but won't you have sort of a greenhouse effect where all the radiation is going to be concentrated, it's going to be overheated? They don't have water?
100% no. It's relatively easy because new materials, you know, now the materials is available in ice. It's called the ice cube. What is it called in Beijing? There are materials that you can control, or the structure you can control the sunlight intake, and so partly because ability of control solar energy, and the stone will become much more efficient. So there's no greenhouse. There will be no, and in theory, you can, if you don't worry about the look.
We would like to see the sun, yeah.
To get out of it is very easy. It's 6 kilometers, it will be rapid transit. The line also have that. Actually, the line has 3 layers: surface layer, first surface layer, and transport layer. I think that transport can be same, but because this is very short, it's only 6 kilometers. So these things we went through, and we are designing.
So, Yuguo, in our field of aerosol chemistry, some people argue that, and they have experiment to prove that when it is in a congested area with lots of people, CO2 increases. And the CO2 partition into the droplets, right? And then make the droplet more acidic than otherwise. And the acidic environment help to preserve or even promote viral growth. So I don't know, in your formulation, have you, I mean, does this concept make sense? I don't know. I mean, yeah.
I think there is a good paper written by somebody from England or UK.
Bristol.
Or US, talking about the acidity.
Yeah.
I think it's very interesting from a different perspective. So far, for my part of work, because I need the source strength to characterize how large is the outbreak. So by doing that, we use the existing outbreak data. So it's indirect estimate. I guess if we understand the survival mechanisms of viruses within the droplets little environment, for them this is a city. So and interacting with surrounding CO2, maybe other chemicals, it will be magnificent, I think, to go to fundamental level to estimate the source. Our source so far is indirect. I feel that it's a little bit unfortunate. So I really look for, we were interested in the work you were doing
well,
at the time.
It's someone, University of Bristol, but anyways, yeah.
Yeah.
Okay, well, if no more questions, you have one? Okay, please. Good to have a student asking questions here.
Thank you. Thank you, Professor, for the interesting talk. And I'm a student from Professor Chuck Chen's group. Yeah. You mentioned the real time in this seminar for several times, but so far I think the sensor for bioaerosols, there is a delay time always, like 2 hours. So it means that if you collect the bioaerosols, new coronavirus, and you need to wait 2 hours for positive or negative results. And do you think this is fast enough, or modeling, if it's possible for you to produce some threshold or standard for different sites, like buildings, like rooms, like hospitals, to say how fast the sensor needs to be to reduce the population, reduce the pandemic? Yeah.
I think the bioaerosol sensor, you mean that if you are able to measure the effectivity and the amount of those viruses in the room, I think some people claim it will be great. Even this 2 hour delay, you can still trace back. If it's 1 day delay, you can trace back. What I talk about the real time is different. I hope to know the ability of a building in dilution, so that if a building, because the individual you cannot control, you cannot say I'm not allowed in this room, but you can say, okay, this room now is risky, and people may choose to leave. Things like that. If we all avoid those poorly ventilated spaces, the pandemic is gone. You do not need to improve anything. You just avoid those spaces. We know most of those spaces are reasonably ventilated for this purpose, as I can see. So that's the purpose. But in order to measure, in Hong Kong, millions of spaces, I don't know how. This is the problem. In billions in the world. So we need a smart way that maybe exists.
Thank you.
With that, thank you very much.
Thank you.